Water's hidden side is revealed. It can exist in two liquid forms at once, according to University of California, Michelle Franklin. Scientists have found that water under extreme pressure and cold temperatures can split into two different liquid phases. This was theorized decades ago but never proven until now. Advanced molecular simulations, leveraged AI, and quantum mechanics have made it possible to model this elusive behavior, hinting at potential future applications in material science and environmental technology. And the unique nature of water. Water is truly unique substance. It's one of the few materials that can naturally exist as a solid, liquid, and gas at the same time under normal conditions. For example, think ice floating on the pond, liquid water beneath it, and water vapor forming clouds above. It's also unusual because its solid form, ice, is less dense than the liquid form, which is why it floats. Now, researchers at University of California, San Diego, have uncovered another remarkable property of water. Under extreme pressure and low temperatures, liquid water can separate into two distinct liquid phases, one denser than the other. This discovery, published in Nature Physics, provides new insight into water's complex behavior. The molecular modeling, a new approach. Francesco Paisani, professor of chemistry and biochemistry at UC San Diego, leads a team that combines chemistry, physics, and computer science to develop advanced models of molecular behavior. Using machine learning and computational algorithms, his group creates highly realistic simulations that closely match experimental observations. Paisani said, "Our water model is so realistic you can almost drink it." Water's critical point revealed. Most liquids are homogeneous. They all flow together and you cannot distinguish one liquid molecule from the next. Indeed, this is mostly true of water. However, in 1992, researchers theorized that at a certain temperature and pressure, liquid water would reach a critical point at which it would no longer be homogeneous. Paisani's team conducted simulations that revealed the critical point at which the temperature is low enough. That's minus 103 degrees Fahrenheit, or 198 Kelvin. And the pressure is high enough, that's 1,250 atmospheres, for water to spontaneously separate into high density and low density liquids. I wonder if that's possible on our Earth, to find, like, for example, an ocean under an ocean. At this critical point, water exhibits wild oscillations between high and low density phases. Below this pressure, water returns to its low density phase, and above it, it shifts entirely to the high density phase. This is an unexpected phenomena unfolding at the molecular level. Advancing computational models. The 1992 simulation was crude. Since then, researchers have tried to create this spontaneous separation experimentally, but without success. Over the past 3 decades, advancements in computational modeling have made more detailed, accurate simulations possible, particularly the advent of data-driven many-body potentials, in which Paisani's group specializes. The data-driven many-body model of water, MB-POL, developed by the Paisani group, is trained on high-level quantum mechanics calculations, data-driven, and rather than calculating the energy of an entire system at once, they deconstruct energy in terms of individual contributions, many bodies. And these reference energies are fed into a machine learning model that is then able to provide realistic simulations of water across the entire phase diagram. Understanding water at the quantum level. Paisani explains the MB-POL model in this way. A person alone in a room behaves a certain way. If someone else enters the room, the first person's behavior changes to accommodate the second person. If a third person enters, the dynamic of the first two changes, on and on until there are so many people in the room that the addition of one more does not significantly impact the behavior of any single person. This is how MB-POL works. In the short range, there are quantum mechanical effects that directly modify the behavior of the water molecules, just as one person influences the behavior of another. However, at a certain point, the effects are averaged out over the entire system, just as adding one more person to an already crowded room does not impact the behavior of another individual. Supercomputers and the future of research. Quantum mechanical simulations can be extremely expensive. You might be able to calculate the energies of 5 or 6 whatever water molecules. Our method using MBPOL and machine learning allows us to run simulations for up to several microseconds, said Paisani. This is something computational molecular scientists have dreamed about for a long time. However, the discovery did not come easy. Running simulations for this research took nearly 2 years of non-stop calculations using some of the world's most powerful supercomputers, including expanse at the San Diego Supercomputer Center, which is a pillar of UC San Diego's new School of Computing, Information, and Data Sciences. Synthetic liquids and future possibilities. In the future, as technology develops, Paisani hopes that research might be used to devise synthetic liquids that undergo a similar liquid-liquid transition as water, but can do so in everyday conditions. Porous liquids that can move from low to high density would behave similarly to sponges and could be used to capture pollutants or aid in water desalinization. The simulation took almost 2 years, so this is a really exciting accomplishment, Paisani said. I think our estimate is very realistic, and now it's up to experimental researchers to see whether our predictions are correct. The challenge of experimental proof. Currently, recreating these conditions in a laboratory remains a challenge. However, nanodroplet technology could offer a way forward by creating tiny water droplets that generate high internal pressure through surface tension, potentially leading to experimental confirmation of this phenomenon. For now, this discovery offers the most accurate prediction yet of a phenomenon scientists have long suspected, but never directly observed. And when that day comes, it may change the way we think about water forever. And this is on SciTech Daily by Michelle Franklin, University of California, San Diego. Please leave your comments, and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.